Hi there, and welcome to Telefunken. Today's video is a bit of a departure from our regular programming, although it's one in a series on the vintage Roland CR8000 analog drum machine. In this part of our series, we'll be using the CR8000 as our guinea pig, where we design, program, install, and test a MIDI kit for this machine using Arduino as our development platform. We'll be documenting the entire process from start to finish in such a way that it could serve as an introduction to using Arduino or other microcontroller systems to interface with MIDI. Whether you're new to Arduino, new to modifying vintage drum machines, or a seasoned pro, I hope to describe the project in sufficient detail for each of you and give you all the information you need if you'd like to do something like this on your own. If this sounds interesting, stay tuned. We'll be using the CR8000 as a prototypical vintage instrument that we would like to control with MIDI. Many of the same principles apply to many other instruments, but are especially relevant when we consider early electronic drum machines. Roland's CR8000 was released in 1981, the year Dave Smith and Chet Wood presented their seminal paper, Universal Music Interface, to the Audio Engineering Society, and MIDI was born. Since MIDI was standardized in 1983, it's been the de facto means of communicating with musical instruments. As cutting edge as the CR8000 may have been in 1981, including its incorporation of DIN-Sync, the inability to control its voices with modern-day sequencing software limits its utility in most studios. A MIDI kit would allow us to more comfortably integrate the CR8000 into today's studios by both syncing the drum machine to a MIDI clock and allowing us to control its various voices using our favorite sequencing software. With the CR8000, we're offered extra motivation for a MIDI solution, in that, while the CR8000 has built-in circuitry for 14 drum sounds, 3 of those are effectively hidden from use in the user-defined programs. While these voices, the clave, high conga, and rimshot, appear in some of the preset patterns, if we want to use them in our own compositions, we may need some way of triggering them. While I'm not aware of a custom MIDI kit designed specifically for the CR8000, at least 2 vendors have developed general MIDI to trigger solutions that can be used. I'll describe these briefly. The 2 solutions that come to mind are Tubitek's Unipulse kit and Kenton's Caddy. Each of these receives MIDI data from a MIDI controller, sequencer, or DAW and converts that MIDI data into signals that trigger the clock and drum sounds on the CR8000. The Tubitek Unipulse consists of a PCB that's mounted inside the drum machine and subsequently configured using PC or Mac-based software to work with the CR8000. Kenton's Caddy solution is an external box that interfaces with the drum machine through a custom cable soldered into place at various points inside the CR8000. The Caddy box is configured to work with the CR8000 using an interface built into the external device. Both solutions are designed in such a way as to maximize flexibility and allow them to be used in a wide range of drum machines with different trigger types, voltages, and waveforms. These solutions differ in the way that they respond to velocity information, with the Kenton responding to accent only, while the Unipulse is purported to offer actual velocity sensitivity on each individual sound. An alternative to these off-the-shelf MIDI solutions would be one that we design ourselves. While it might be tempting to think of this approach as being more cost-effective than the bot solutions, this is only true if we fail to take into account the value of the time required to design, build, and test our own MIDI kit, which will more than offset the monetary savings of building our own MIDI to trigger converter for the CR8000. But it's not about the money. We're in this to learn and have some fun, so let's explore this idea further and see where it takes us. First, we'll ask ourselves what we actually need in a MIDI kit. What are our baseline design specifications? We're actually not asking a lot. First and foremost, we need the machine to recognize and respond to MIDI start, stop, and clock information. And we know it already contains the logic circuitry required to track to DIN-Sync. We need to be able to trigger the drum sound sent to the instrument through MIDI, but we don't need to be able to remap the MIDI notes used to trigger each individual drum sound, as we can work with a predefined map within our DAW. Nor is it necessary for us to have true velocity sensitivity on each individual drum sound, though it might be nice to be able to take advantage of the existing accent function in the instrument. Ideally, though, we'd like to be able to specify the instrument's MIDI channel, so we're not interfering with signals sent to other MIDI instruments in our MIDI chain. All of the things on our wish list can be accomplished in a relatively straightforward manner using a dedicated microcontroller. With the appropriate programming, a microcontroller could be used to read and interpret both MIDI timing data, the run, stop, and clock signals, and the drum note, on and off information. A microcontroller could be used to translate the MIDI data stream into a format that can be used by our vintage drum machine's existing timing circuitry. In this way, we could control the machine's tempo in sync with our DAW and trigger notes using drum triggers generated in response to the MIDI notes that correspond with the drum sounds in our MIDI map. We don't need a lot of processing power, at least by today's standards, to accomplish this. We're processing MIDI data, 8-bit data transmitted serially at 31,250 bits per second. This data stream is readily processed by the 8-bit ARM microcontrollers, such as those used in the Arduino family of microcontroller boards. Using Arduino offers a number of other advantages. If we develop our system within the Arduino framework, we can leverage resources available to us, including the Arduino Integrated Development Environment, or IDE, and the Arduino MIDI software library that will further expedite our development path. In case you're unfamiliar with Arduino, Arduino is, first and foremost, the name of an open-source hardware and software development company. They design and manufacture single-board microcontroller devices, colloquially known as Arduinos. These devices can be programmed within the Arduino IDE, itself a piece of software that runs on your PC, using a version of the C++ programming language. In combination with various expansion boards or interfaces called shields, Arduinos can be used to digitally interface with and interact with their environment. Arduinos come in many varieties, often utilizing different microprocessors and ancillary components. The same microcontrollers used in any given Arduino can be obtained in individual chip form, and with a small set of ancillary components, the microcontroller can be made to run code written and developed on a full-blown Arduino board. This hints to the development path we'll be taking with this project. We'll start with a proof of concept using an off-the-shelf Arduino. This board will have all the components required not only to operate the microcontroller, but to interface with the integrated development environment running on a PC. This is accomplished using a second onboard microcontroller that functions as a USB interface. We'll use this interface to load the software we'll be writing for the Arduino using the IDE. This facility and its relative ease of use have been part of what has made Arduinos so popular. Once we've convinced ourselves that the project is viable, and that we can both sync the drum machine to MIDI clock using the Arduino's microcontroller, and that we can receive MIDI drum notes and convert them to CR8000 drum triggers, we can port the software over to a breadboard prototype built around the microcontroller chip alone. Once that's working, we can design a dedicated PCB that will be mounted in the drum machine and function as our MIDI to trigger converter. The final project won't be USB compatible, so we'll need to program our microcontroller using the microcontroller's in-circuit system programming capabilities. Now, all of this might sound a bit daunting, but I'll let you in on a little secret. I'm far from an Arduino expert, so if I can pull this off, so can you. There might be other or even better ways of accomplishing what we're trying to do here, but the results we're going to achieve will speak for themselves. We're going to learn a lot and have some fun along the way. Before we start designing around a specific microcontroller chip, we need to achieve proof of concept with an Arduino, and our first challenge is getting MIDI data into the microcontroller. In this regard, the internet is our friend, as there are plenty of examples online describing Arduino MIDI projects, and there are a couple of great YouTube channels dedicated to the subject. However, one thing you'll notice right away is that most people are describing applications that use Arduinos as MIDI controllers, systems that take real-world analog input and convert it and output it as MIDI data, used to control virtual instruments or a DAW. In our case, we want to accomplish the exact opposite. We want the Arduino to read incoming MIDI data and use that data to control a physical instrument. So we need a suitable MIDI input circuit rather than one that outputs MIDI data. MIDI input circuits are just a little more complicated than MIDI output circuits, as we'll see in a moment. The second thing you might notice is that for some reason, the vast majority of MIDI circuits described for Arduinos utilize the 6N138 opto-isolator. Opto-isolators are an obligate component of any MIDI input circuit. Their role is to electrically isolate each piece of MIDI gear in a MIDI chain and prevent damage to electronic components if any one piece of gear in the MIDI chain should fail. Although the 6N138 was originally specified as a suitable opto-isolator for use in MIDI input circuits, it's a pretty slow chip, and in this context, it's operating at the limits of its performance specification. It's now considered obsolete and is no longer available from some supplier. A much better solution for use in MIDI circuits is the closely related opto-isolator, the 6N137. The 6N137 is a much faster chip that operates more comfortably at the standard MIDI baud rate, but it does require some minor changes to the supporting circuitry to function as a MIDI input device. I mention this only in case you're following along at home. If you insist on using a 6N138 opto-isolator, you'll have to make some changes to your input circuitry. An example Arduino MIDI input circuit is shown here. MIDI data enters through pins 4 and 5 of a standard MIDI cable, the MIDI current source and current sink, respectively. Roughly 5 milliamps of current activate the LED in the 6N137, which is in turn recognized by the internal photodiode. The 6N137 has an internal comparator, and the MIDI data is presented to pin 6 of the opto-isolator. This serial data stream can be passed directly to the Arduino serial data receive pin, labeled RxD in this example. So as you can see, with only a handful of components, we can get MIDI data into the Arduino. What we do with that MIDI data will be a matter of programming, and we'll return to that in a moment. But in the meantime, we know we'll need to interpret that data in such a way that we can present it to the drum machine in a format that will be useful. We have 3 types of MIDI data we're interested in. First, we have MIDI start-stop data, which unsurprisingly tells the instrument when to start playing and when to stop. Second, we have MIDI clock data, which is the data that keeps the various MIDI instruments that are running off their internal clocks in sync with one another after they've received the MIDI start signal. We're going to use these 2 types of data to sync the drum machine to MIDI clock and keep it in time with the rest of our studio. The third type of MIDI data we're interested in is the MIDI note data, the data that tells us when to play a drum sound. This third data type is read independently of the sync data. In fact, we want to be able to play or trigger the drum machine's notes over MIDI even when the MIDI clock hasn't been started. We'll come back to the drum triggers in a moment while we focus our attention on the sync. The CR8000 has its own internal clock and built-in DIN sync circuitry, most of which is located on the CPU board. The machine sends and receives DIN sync through 2 pins on a 5-pin DIN connector, a connector that looks just like a MIDI connector but works in a very different way. One pin, pin 1, carries the start-stop signal, while the other, pin 3, carries the DIN sync tempo clock. The DIN sync send and receive functions are selected using a switch on the back panel of the machine. When in the send position, the CR8000 generates its own start-stop and clock signals that can be sent out the DIN connector to drive other drum machines or synthesizers, such as the Roland TR606 and the TB303, that have similar DIN sync capability. When in the receive position, the CR8000's internal clock circuitry is disconnected from the CPU, and the machine waits until it receives an external start signal before running in sync with the incoming clock data. Most DIN sync capable instruments have similar sync circuitry. DIN sync is much simpler than MIDI data. While MIDI data is 8-bit data, and some MIDI messages may take as many as 3 bytes, the DIN sync start signal is simply a logic high at pin 1 on the DIN sync connector. DIN sync clock data is similar. The clock signal is a positive logic pulse 24 times every quarter note, hence the term 24 PPQ, which denotes 24 pulses per quarter. Some instruments have the ability to use 48 PPQ DIN sync. If you ever find your DIN sync gears running twice as fast or twice as slow as you were expecting, chances are you have a mismatch in your DIN sync chain. Since we're going to be using the MIDI clock to sync the drum machine, we'll have the sync switch in the receive position, thereby disconnecting the rest of the sync circuitry. We need the Arduino to read and interpret the incoming MIDI clock data and send it out to the drum machine in a way that mimics the normal DIN sync signals. This is even easier than it sounds, in part due to the existence of code libraries that have been written to recognize and interpret MIDI data received on the Arduino serial bus. We simply need to choose a general-purpose I/O pin on the Arduino that we'll use for start-stop signals, and another we'll use for clock. We'll ask the Arduino to listen to the serial bus, and when it recognizes a MIDI start signal, we'll tell it to set the start-stop pin to logic high. When the Arduino receives a MIDI stop signal, we'll ask it to set the start-stop pin to logic low. Similarly, when the Arduino receives a MIDI clock signal, we'll have it send a short pulse to the clock pin. If we connect these pins to the CR8000 at the appropriate points, where the drum machine is expecting to receive the DIN sync data, we can sync the drum machine to MIDI. Although we could connect the Arduino directly to the DIN sync connector, we'll use attachment points on the more accessible top surface of the CPU board and connect the start, stop, and clock signals to the terminals of R56 and R58 respectively. We now have to figure out how to trigger the individual sounds or voices in our drum machine. Triggers are generated by the drum machine's CPU in response to the patterns stored in the drum machine's memory. Each trigger is then individually buffered by a 4050 non-inverting hex buffer before being passed to the voice generator board. Vintage synths and drum machines typically use one of two different trigger types. In the first case, a positive going voltage pulse, a so-called V trigger, activates the instrument's voice generation circuitry. The default state of the voltage trigger circuit is a logic low, or 0 volts. In the second case, a so-called S trigger can be thought of as the opposite of the V trigger. S-trigger circuits are nominally held high, around 5 volts. The trigger is the negative going edge of a negative going pulse, which is achieved either by an actual short or in some cases simply a logic low. It's the latter type of trigger that our drum machine is expecting. The CPU in the CR8000 nominally holds each drum trigger at 5 volts. Then in response to a programmed note, the CPU sends a signal that causes the trigger voltage to go low. The duration of the trigger signal is determined by the tempo of the drum machine and can range from 4 to 70 milliseconds. In the CR8000, the entire voice sounds as long as the trigger of sufficient duration is received by the voice generation circuitry. Although the voice circuits themselves are spread across the entire voice generator PCB, the triggers leave the CPU board via one 15-pin connector. This gives us a convenient access point that we can use to trigger each of the 14 voices in the drum machine, as well as the accent, which uses the same S trigger. Before we get started with building a prototype using Arduino, we have a couple of other things to consider. It would be nice to be able to have some real-time feedback as to the operation of our MIDI converter. So in addition to using the Arduino's GPIO pins to send signals to the drum machine, we can also connect LEDs to these same pins that will indicate when the Arduino is sending a start signal and when it's sending clock data. We'll add another LED to a third pin to indicate when we're receiving a MIDI note that corresponds to a drum sound, which will be mapped to one of 14 notes that will eventually map to each individual drum sound. We'll also use the Arduino's onboard LED to indicate the receipt of any MIDI note, which will help us in troubleshooting in the event that we're unable to trigger drum sounds on the CR8000. You notice I haven't said a word about programming the Arduino. Don't worry, we'll be coming back to that in a moment. First, let's build our MIDI input circuit and connect a few LEDs to our Arduino and see if we can get it to read MIDI data and generate triggers that our drum machine can use. So I'm using a Arduino Uno R3 as a starting point for the development of the trigger. And what I have is I have it connected to a breadboard, which has a MIDI input with an optocoupler. And I've got as well a number of indicator LEDs wired in. In the first case, the onboard LED is indicating receipt of a MIDI note. The green LED is indicating a start-stop signal. And the blue LED is indicating a clock signal. And the red LED is indicating the receipt of a drum note. I've also got this graphical multimeter connected, and it is set up to be a single shot capture oscilloscope. What I'm going to do is hit a drum note. There we are. You may be able to see the single shot that's been captured. And what we can see is we can see a signal that is held high at approximately 4.9 volts. And then upon receipt of a MIDI drum note, the signal goes low to essentially 0 volts. And this has a duration, which is established by the program in the Arduino, of about 5 milliseconds. Now, the MIDI note is triggering a drum when it's in the range of notes that have been programmed into the Arduino as corresponding to drum notes. And those are the notes between C1 and D2. Now, if I go outside of that range and I hit a note, we still are receiving a MIDI note, but it's not triggering a drum. If I press run start, we see that we have the run light indicating. We see the trigger is lit, and we see that we're receiving drum notes, which are programmed into a sequence on the Arturia BeatStep Pro. If I reduce the tempo, and if I reduce it low enough, you should be able to see that the trigger, the clock signal, is actually blinking much more slowly. That's still 24 ppq, pulses per quarter, but we're at a tempo of 30 BPM. So that's 1 beat every 2 seconds. So now we're looking at 12 flashes of that light per second. We can bring that back up and it will look like it's constantly lit, even though it's not. And there we go. Again, we can trigger drum notes ad hoc when the sequencer is running. So according to this test and these LEDs, this is working more or less as it should. The next question is, can we actually use this setup to trigger the CR8000 and to keep it in time with the clock? So what I've done now is I have connected the ground of the CR8000 to the ground of the Arduino, and I've connected the trigger out pin of the Arduino to the trigger out pin on the CPU board for the clap. And what I can do is I can trigger using the BeatStep. I can trigger the clap sound by hitting any of the pads that are sent to a drum, because right now they're all sending out to this one pin. And so that appears to be working. If I send a MIDI note to the Arduino that does not correspond to a drum, the drum doesn't sound. So again, that seems to be working. If I play the sequencer, we're getting the clock signal, etc. And because the sequence contains a drum note, we're hearing it. And of course, we can control the tempo. What we have not yet done is connect the clock and the start-stop to the CR8000 to facilitate control of the start-stop functions on the instrument so that we can sync it. This triggering approach, however, would be adequate to facilitate MIDI control of the individual sounds. What we've done now is we've connected the start-stop signal, which is this green lead here, to the lead of R56, where it connects to pin 1 on the sync in-out jack. And we've connected the clock signal, which is this black wire, to the lead of R58, which is the resistor that's connected to pin 3, the tempo clock signal. And we've got the instrument on sync in, which means that it's waiting for a sync signal before it actually starts. And I've selected a pattern, and you can see that it plays, and that we can control the tempo, and we can start it and stop it. If we turn the pattern off, all we have now is the signal sent by the pattern that's in the sequencer. However, we can synchronize our accompaniments. We can even introduce shuffle on top of that. You get the idea. All that remains now is for me to adjust the program so that instead of just sending one drum note for all the various pads that are consistent with drum notes or expecting drum notes, it'll send individual drum notes to individual triggers. And so this is where we require a microprocessor, a microcontroller with a lot more digital outs than the one in this Arduino Uno R3. And so it'll require some different hardware, some different programming, and also I'd like to be able to select the MIDI channel, because right now we're receiving on all channels. We're in Omni mode. And I think that this device deserves the ability to be able to select the MIDI channel. So a little bit more hardware development, and we'll be right back. So our proof of concept with the Arduino seems to work well. But how did we interpret the MIDI data coming into the Arduino, and how did we use it to control the drum machine? This is a matter of programming, and we'll describe the various elements of our prototype's programming now. We'll assume some level of familiarity with the Arduino IDE, and that you already know how to load an Arduino sketch into the Arduino. If you have any difficulty, there are plenty of resources online that can help you with the basics. The first thing we need to do in our Arduino sketch is include the Arduino MIDI library. Using the Arduino MIDI library is the most straightforward way to add MIDI input and output capability to an Arduino board. The MIDI library contains functions that handle MIDI messages of all kinds, including the MIDI clock data that we'll be using to synchronize our drum machine. If you don't have the Arduino MIDI library installed in your IDE, you can download a copy from GitHub, where you'll also find instructions on how to install the library using the Arduino Library Manager. The first line of code, include MIDI.h, tells the IDE to include code from the MIDI library in the compiled code at compile time. The next few lines of code define the GPIO pins that we'll be using in our sketch. We'll use 4 of these to power indicator LEDs that will show us that our program is working, while the 5th, pin drum trigger, will be used to send a negative going S trigger to the drum machine. The last line of code on this slide creates an instance of the MIDI library using the default serial port settings. With the library included and pins defined, we can enter the setup subroutine, a section of code that will be run once and once only. Here we establish the mode of the GPIO pins we'll be using so the Arduino knows they're going to be outputs. We initialize these pins, turning off 3 of our LEDs and setting the drum trigger output high, the default state for an S trigger output. We then tell the Arduino to begin using the code in the MIDI library to listen to the serial port in Omni mode, that is, to respond to MIDI messages received on any one of the 16 MIDI channels. We then have to tell the Arduino what to do with each type of MIDI data it receives. The MIDI library uses callbacks to call a specified function in response to certain MIDI events. Here we're telling the Arduino to call our user-defined functions in response to incoming MIDI note on, note off, and timing data. The main program loop, consisting of a single line of code, is shown here. The command MIDI.read tells the Arduino to look at the serial port and read any incoming MIDI data and repeat. What it does with any of the data it receives is determined by the functions called in response to the various MIDI data types in the callbacks. Here we have 4 functions that are called in response to incoming MIDI data. The first, handle start, is called in response to the Arduino receiving a MIDI start message. When we receive the start message, we set the start-stop pin high, emulating the behavior of the DIN sync circuitry in the drum machine. Notice we haven't had to write any code to parse the incoming MIDI data. We haven't even needed to define what a MIDI start message looks like. All of that work has been done for us already by the authors of the MIDI library. Our next function tells the Arduino what to do when it receives a MIDI continue message. We'll handle this in exactly the same way as a MIDI start message and set the start-stop pin high. It shouldn't surprise you to see the next function, handle stop, again simply emulates the behavior of the DIN sync circuitry and sets the start-stop pin low, telling the drum machine to stop its internal sequencer. The last function, designed to handle clock data, is a little different. In this case, we want to generate a positive pulse at the clock pin, so we set the pin high in response to an incoming MIDI clock data signal, but we don't want to leave it hanging there. We want to generate a clock pulse that's just 4 milliseconds long. In this example code, we've used the delay function to accomplish this, a function that should be familiar to you as it's used in the Arduino's Hello World equivalent, the famous blink sketch. The delay function waits for 4 milliseconds before the Arduino turns off the clock pulse by setting the clock pin to low, thereby ensuring we're ready to send the next pulse. The code we're using to handle drum note data is just slightly more complicated. The first line turns on the Arduino's power LED, which we're using here to indicate that we've received MIDI data. The if statement tells the Arduino to pay attention only if the note is in the range of MIDI note values that corresponds to the notes used in our MIDI drum map. If the note is a bona fide drum note, the drum note LED is turned on and the drum trigger pin is set low, the active state for the S trigger used in the CR8000. Here again, we want to generate a pulsed response to the drum note, so we wait 5 milliseconds before turning off the drum trigger and the drum LED. The last function handles the note off messages, and in this case, it turns off the Arduino's power LED so that it can be turned on later and we know the Arduino is receiving MIDI data. While this code may be perfectly adequate for our initial prototyping purposes, and it is the code we've used in the example shown in the previous section of video, it contains two major flaws that should be obvious to many of you. The functions that handle clock and note on data both rely on the use of the delay function to generate timed pulses at their respective GPIO pins. However, it's important to recognize that while these functions are being executed, the Arduino is unable to do anything else. It simply waits. While a 4 or 5 millisecond delay might not seem like a lot, in the musical context, it is significant, and in the context of the microprocessor's capabilities, it's an eternity. Given that the Arduino can execute around 1 million instructions a second, it's the equivalent of taking a road trip with your family and being asked, "Are we there yet?" 4,000 or 5,000 times. If we examine just the clock pulses, for example, at 24 ppq and 120 beats per minute, we're asking the Arduino to spend 192 milliseconds of each second, almost a fifth of the time, waiting for clock pulses to finish. If we consider the drum triggers, with this code we would have a 5 millisecond delay between drum sounds that were programmed to sound at the same time. So clearly, we need another way of generating timed data pulses that won't bog down our microcontroller, otherwise we won't be able to keep time with the MIDI data stream, which is sort of the whole point of the exercise. One way to overcome this issue is to time the pulse duration using the Arduino's millis function. An example using milli to determine the clock pulse duration is shown here and compared to the use of the delay function. The millis function is used to grab the precise runtime from the microcontroller, a measure of how long since the microcontroller booted up. Rather than simply waiting for the pulse duration to be over, as is the case when we use the delay function, we can use millis to tell us when we started our clock pulse. We then move on and execute other code, and from time to time check back to see how much time has passed since our clock pulse began. Once we've exceeded a predetermined pulse duration, we end the clock pulse. The key here is that once we've started the clock pulse, we've freed up the microcontroller to run other code, including the code that tells it to listen for more incoming MIDI data and play our drum notes. The way this is implemented is shown here, where we've added two additional functions to our main loop. We read the MIDI data, then check to see if we need to turn off a clock pulse, then check to see if we need to turn off a drum trigger, and repeat. So although this code has served its purpose, we know that we have a number of improvements we need to make before we can have a program that does everything we want. First, we'll replace the delay function with code that will use millis to avoid bogging down our processor. We've already mentioned that we would like to have the user select the MIDI channel that the MIDI to trigger converter will use. One way to achieve this is to set up an array of 4 switches that the Arduino will read as inputs and decode to select one of 16 MIDI channels. As these switches will eventually be mounted on our PCB, which will in turn be mounted on the inside of the drum machine, we might want to have a way of indicating which MIDI channel has been selected, so the user doesn't have to remember or guess which channel is being used by the drum machine. To do this, we can take advantage of the indicator LEDs that we have included in our design, as well as interfacing with some of the indicator LEDs that are already built into the CR8000 drum machine. The last addition to the program will be converting it from a simple program that sends out an S trigger in response to a drum note to a program that sends out one of 15 different triggers in response to defined pre-mapped drum notes. This will require the use of a microcontroller with several more GPIO pins than the one we have used here, and this is something we'll cover in future videos in this series. So in this, our first installment in the series, we've demonstrated proof of concept for our MIDI to trigger converter using Arduino. We've shown we can use the Arduino and the Arduino MIDI library to read incoming MIDI data and output DIN sync and S-trigger data in formats that can be used by our vintage drum machine. In future videos, we'll tackle some of the issues we've just talked about and build our next prototype on a breadboard. Once we have the hardware down pat, we'll design a PCB, build it, and assemble the final project in our drum machine. If this sounds interesting, stay tuned and consider subscribing. And as always, thanks for watching.